I'm recording this, by the way. So yeah,
Okay.
I'll record for you. Yes.
Sorry, I got a little bit of a frog in my throat today, so hopefully that won't be too much of an issue. So let me go right into the screen sharing here. There we go. Okay. So I'm going to introduce you to my software, and I thought maybe I'd start by introducing myself a little bit. I've been a lifelong amateur astronomer going back to when I was a kid, and that led me to pursuing a bachelor's degree in astronomy at San Diego State University. And I went on to get a master's degree there in astronomy as well. And then I went to Ohio for a PhD, and that didn't work out so well. I didn't really match right with the program there. Sometimes you make decisions in life and, oh wow, somebody's calling me. Sometimes you make decisions in life and they don't work out. So I took a master's degree in astrophysics from there. So I actually have 2 master's degrees. While I was there in Ohio, I started developing software for the PC, and I created a product called PC Sky. And that did a simulation of the sky, sort of a natural simulation, showed what you'd see in a telescope and things like that. This was a long time ago. And after I left that program, I went back to San Diego and I got a job with working for Mike Malin, who's a planetary scientist. And at the time, there were only 5 of us in the company, and we were developing a camera to fly on the Mars Observer spacecraft. And that was pretty awesome to do for a couple of years. And I started selling the software that I'd written. Excuse me. And then as the spacecraft entered orbit, we lost it. And that meant my funding went away from my job. And at that point, I was already thinking of moving on. So I created my own business, which I call Skyhound, to sell astronomy software. And what I did is I started thinking about what could I do that would be really useful. And I had been involved in planning software for many, many years for planning observations. So I thought maybe we could bring that kind of planning from the professional world to the amateur world. So I started working on what would become SkyTools while I was teaching astronomy at a local community college. And I got behind on my slides already. Here we go. So, and from there, after doing that, starting my business, I moved to Cloudcroft, New Mexico, which is at about 9,000 feet. And this is a picture from yesterday, or a map from yesterday, a fire map of southern New Mexico. And I live in Lincoln National Forest over on the right, way up at the top of the mountain, just under 9,000 feet. New Mexico Skies is about 13 miles away. So I'm very close to the New Mexico Skies iTelescope site. You can see a big red patch on the left over there. That's an 80,000 acre fire in the Gila Wilderness. And you may have noticed that the New Mexico Skies has been closed recently because as the weather changes in the evening, the smoke from that fire blows right across, and it looks like clouds. And they're not there during the day, which is really odd. You can see that we're this green area here in Lincoln National Forest on the right is the only major forest that hasn't had a major fire yet. Yesterday, the humidity was 7%, and our fire danger is extreme. So what I did is I started this thing called SkyTools, and it came out in 1999. And then SkyTools 2, which is what we're showing here, came out in 2003. So I've been doing this a long time. And in fact, it was probably 1995 I started the first code. 2008, SkyTools 3 came out, and that was a big deal. That was really the first time I felt like I'd reached what I wanted to accomplish. I added some imaging features, but mostly it was for visual observing. Excuse me. And when I went on to make SkyTools 4, I wanted to really get into into imaging. And it turned out in order to do that well, I had to create a separate product. So I split SkyTools into one product for visual observing and one product for imaging. This is SkyTools for imaging, and it came out in late 2017. So the basic idea behind SkyTools imaging is that you're all familiar with processing your images and how technical that is and how difficult it is to get a good image. And the idea is that on the other end of that is the image capture to begin with. And the idea is to have the highest quality data possible from the beginning, and that will allow you to get the highest quality images in the end. And it's also mixed into that is the idea of efficiency. So you get the most data as possible. These are the goals of SkyTools imaging. So in order to do that, I developed an imaging system or a workflow. And it starts with selecting an appropriate target. And for that, you want something with a good image scale. If it's only 2 pixels across, it's not going to be very interesting. And you want to be able to obtain a reasonable quality image in a reasonable amount of time. Some tiny faint nebula or some large faint nebula, it may be that your imaging system can't even detect it, or maybe it can't take a high quality image. So selecting an appropriate target is the first step towards success. And you'll hear me use the term imaging system, and that is the entire package, not just the telescope, but the camera and its detector and even the weather conditions, the filter, all of that is part of your imaging system. So the next step is to create an imaging project. And this is where you define what you want to accomplish. So you select what filters you want to use, maybe what sub-exposure times, total exposure time, and so forth in this project. And then you go observe that project in step 3. And step 3 is to use the SkyTools scheduler, where it will help you observe that project at the optimum time on a given night. Then for a multiple night project, if you're doing a 10-minute exposure on M42, it doesn't really matter. But what if you're doing a project like we were just talking about, that's multiple nights, many hours, maybe 100 hours? You need to keep track of what you've already accomplished so you know where you're at, especially if you're trying to reach a particular signal to noise ratio. So you track your observations as they're completed. That's step 4. And then when you're done, you have a completed project that becomes an archive, a searchable archive. You can go back and see what images you took and when. So that's the basic workflow. And here's another view of it: target selection, project goals, scheduling, and then tracking. So target selection is usually just what's good for my telescope, what'll make a good image. Project goals are what I want to accomplish. Scheduling is on a given night, what's the best time to observe that object and get my images, and then finally progress tracking. And you'll hear me use the words observing and observations, and that's because I'm an old-time astronomer. I'm an observational astronomer. I know that people in the imaging community these days have started using the term observing to mean visual observing, but really observing is any kind of observing. So I'm going to stick with that, and you'll hear me talk about observing. That also means imaging, and your images are your observation. The problem with all this is, how do you do that? Because every imaging system is unique. Every one of these telescopes here has different characteristics, and there's no one size fits all to get what you want. To understand your imaging system fully, you have to understand each one separately. So the latitude, the elevation, the amount of light pollution, aperture and F ratio, the optical system, the detector, the pixel size and number, the noise quality, spectral sensitivity, filters that are available. That all determine the image scale, which can determine the faintest thing that you can record, and so on. And then on a specific night, the weather conditions, how high the object is in the sky, whether there's twilight or moonlight, these are all factors too. For instance, narrowband filters aren't affected by twilight as much. So, hold on just a second. So narrowband filters, I lost my window. I guess it's just not here anymore. Sorry, excuse me for that interruption. And narrowband filters aren't affected by twilight, moonlight as much. But how much is too much, right? It would be nice if we had an answer to that question. Then we could pick a telescope and say, I'm just going to do an O3 filter tonight from 11 to midnight because I'm going to get a good result. So in order to do that, you have to understand what the signal to noise ratio is, because it's the key to everything here. And the signal to noise ratio describes the quality of the measurement or the image. So the best way to think about signal to noise ratio is I want a high quality image. I want to have the highest signal to noise ratio possible. Excuse me. So here's an example of signal to noise ratio. We've got on the left, it's a single 3-minute exposure. I think I used T5 for this. That's M81. You can see all this pixelation noise in the background. That's the noise, right? The idea is as you add signal, you drown out the noise and you don't see it anymore. And that allows you to have a much nicer looking image. So you increase the signal to noise ratio, you get a nicer looking image. In the middle here, that is 2 3-minute exposures stacked. You can see already there's less noise in the image. And then on the right, that is 10 3-minute exposures stacked. So one thing you can see from this is that we didn't really find any fainter stars for the most part after we stacked the first set of images. There are some fainter stars coming through, but mostly what we've done is we've taken what we captured to begin with, and we improved it. So stacking images increases the signal to noise ratio. So here's where SkyTools really does its thing. It does something that no other commercial software can do. There are professional observatories use this sort of technique, the big giant ones. But I thought I would bring this to the amateur world. So what SkyTools does is model the signal to noise ratio. So it has to model all of those things that we've been talking about in order to estimate the signal to noise ratio. So what targets in my telescope and camera are appropriate for a good signal to noise ratio? What time of night is the best? And maybe what sub-exposure time are the best? Those are the 3 main things. If we can calculate the signal to noise ratio for any given time, we can answer those questions. So this isn't a technical talk, so I'm going to go through this fairly quickly. Just a second, I've got sort of a technical issue. Excuse me. Okay, so I'm just going to breeze through this. The first thing is the atmosphere. You know, the light from your target object crosses millions of light years and untouched, and then it hits the atmosphere, and the atmosphere scatters the light, it absorbs light. So by the time it reaches the ground, it's been changed. It not only is it changed in that there's less of it, but the color have been changed. So there's a sort of a fingerprint, a spectral fingerprint on the light that's created by the atmosphere as it passes through. And depending on how high the object is in the sky, that's going to determine how much of an effect there is. We define something called air mass, which is looking directly overhead. We call that 1 air mass. at an altitude of just 30 degrees, we're already at 2 air mass. So now we're looking at through twice as much air. So it has twice as much effect on everything. And then it increases quickly after that. So the general rule of thumb is you never want to image below 2 air mass most of the time. Then on the right, there's the seeing versus air mass. And seeing, astronomical seeing in imaging is really pretty much tells you the size of your stars on the image. And that increases pretty quickly as you go closer and closer to the horizon. So what SkyTools can do is it can model those things so that you can get a handle on what kind of image you're going to get, depending on how high you are above the horizon or what the weather conditions are. Then the light passes through your telescope optics, and the telescope optics also leaves a fingerprint on the light, changing the color subtly. This is a very old chart. Don't freak out because of these guys down here. This is where I just basically discovered this effect. I think it was back in 2014. And that is for a reflecting telescope. The longer it's been since the mirror was cleaned, the more performance loss there is. So this is actually, this line here was calculated by an experiment that was done at Magdalena Ridge Observatory, which is here in New Mexico. And they're the only ones who've ever studied this. This is for commercially coated mirrors like we all use. And what it says is that after just 2 years, we've lost 20% of the performance, 20% of the signal from the telescope tube. And ignore these values down here. That was true 14 years ago, but don't look at it and say, I'm never going to use T11 because it's only operating at 22%. That's no longer true. So then we run it through a filter. And this is an example of a 3 nanometer filter for O3. The O3 line is in the middle. And that has a huge fingerprint. Now we're blocking all the light to the left and right of that O3 line. And where this gets, the advantage of this is we're blocking out all the light from the sky outside of that area, but passing all of the light from the O3 line. So your filter matters. Then it finally hits your camera detector. And this is sort of an extreme example of how this particular detector responds versus wavelength. So this is color across the bottom. You see over here on the blue end, this is blue on the left and red on the right. On the blue end, you are more sensitive to light than you are way out here in the red. So you have to put all these things together to model the imaging system. So without iTelescope, I could have done this because there are so many different kinds of telescopes that iTelescope allowed me to test across a variety of different systems to make sure that the model was working properly. So getting back to the workflow here, the first thing you want to do is select a target and one that's suitable for your imaging system. So you want it to be detectable, you want it to have a good image scale, you want it to pass high enough in your sky. Well, how high is high enough? Well, now that we can look at the signal to noise ratio we can calculate how high is high enough. And can I achieve a useful signal to noise ratio for this faint nebula in a reasonable amount of time? And one of the things that comes in here is that there's a trade-off between image scale and the signal to noise ratio. You imagine the target has only 2 pixels, maybe a very wide field view of M42 has 2 pixels. Then all of the light from M42 are going into 2 pixels. Now you spread that out over your detector, and it might be being spread out over 1,000 pixels. So each individual pixel gets a smaller portion of that light. So you've got to have a way to trade off the large image scale with still being able to produce a nice picture. So there's 2 ways you can go about this. What most people do, they've only got one imaging system, so they choose a suitable target. And SkyTools uses what's called the target selection tool to do this. and it's list-based. We're going to do an example of this later on. And what it does is it allows you to filter out target objects that aren't suitable for your imaging system, either in general or on a specific night. So it'll help you pick a suitable target object. Something that's really useful for iTelescope is that you can compare imaging systems. This is the compare imaging systems tool. So in this case, we're going to turn it around. We're going to say, for the helix, which imaging system is the best? And then it's going to rank them. So the one at the top is T17. But with that one, we're going to have to make a mosaic because it's so big. Then there's T9. And what this means is I can get the signal to noise ratio I asked for of 30 in 40 minutes. That's pretty good. And it's 352 pixels across. If we go down to T31, it's going to take 80 minutes, which is why it's ranked lower, but it's much bigger across. This is that trade-off that we were talking about. So actually for me, 80 minutes isn't too long. I would probably go ahead and choose T31 for this. Look down at T30, it's going to take 7 hours, almost 8 hours, but it covers many more pixels. Again, it's that trade-off. Well, another thing you can do is you can look at the imaging quality throughout the night. Now that we can calculate the signal to noise ratio at any given moment in time, what we can do is compare that to the signal to noise ratio we would get for that telescope at that location on an ideal night. And that gives us a measure of the quality. Excuse me. So I'm going to zoom in on this for the helix. So the background of this is called the night bar. The background of this is shaded by the sky brightness model that SkyTools uses. This teal line here is the altitude of the moon. You can see the sky is brighter over here than it is over here on the right. The red dashed line is the altitude of the Helix Nebula. You see it's highest in the sky just before dawn. But the most interesting thing here is this blue line. The blue line is the relative imaging quality. So if you take a 5-minute exposure and you calculate the signal to noise ratio you would get for your target object, compare that to the ideal. If you tried that at 10 o'clock, the moon's up, it's too bright, and it hasn't risen yet, so you're going to get 0. At 11 o'clock, it's very low in the sky, so you're going to get a very low quality. It isn't until you reach about 4:30 that you get a good high quality for the night. So the higher this blue line is, the higher your quality is. And the bar down here at the bottom separates the night out into parts. This dark green is from here, from 2 a.m. to 5:30 or so, or 5:50 maybe. That dark green is the pretty good period of the night, and the bright green is the very best period of the night. So what you'd probably want to do is you'd probably want to start imaging at 4:30 for this object, and then stop at 5:30. So this is how we can use this signal to noise ratio calculation to tell us what the best time of night is to observe our object. So this brings us to the third topic, and that's sub-exposure times. Sub-exposure times are an extremely complex subject. And because there's a lot to it. It's not a simple thing because there's a lot of factors, and in the end, you have to decide what's best for you. And there's no way to do sort of a one button press, what's the best signal to noise ratio. Although SkyTools does that, there are other factors that we need to consider. So what the sub-exposure time does is it determines the faint limit of your final image. It determines the how big and the bright stars are they saturated or whatever. And one way to look at it is if you take one image, this isn't universally true, if you take one image, kind of like what we saw earlier when we were looking at signal to noise ratio with M81, that's going to determine, the sub-exposure time is going to determine what we're going to be able to capture and then stacking more and more of those images increases the signal to noise ratio to make it look better. So this is my rule of thumb. The best sub-exposure time is always as long as possible, except when it's not, which is, there are lots of reasons why it's not. I got a DSLR last year, and I wanted to know how well it would work for astrophotography. In particular, I wanted to see what I could capture for a without a tracking mount. So this is my first image I took. It was 6 seconds. You can see this is of Sagittarius. It's captured some stars. Here's a 12-second exposure. It's captured more stars. So increasing the exposure time has captured more signal. And here's one at 30 seconds. Now we're finally starting to see some Milky Way, this cluster on the right. 90 seconds is where it really pops. So, of course, I'm going to need a tracking mount because I can't go 90 seconds even at this image scale and not have the stars trail. But the thing is, I already knew that because SkyTools had told me that. And here is 120-second exposure, 2 minutes. And now you're starting to pick up some sky background. And so anywhere above 90 seconds to 120 seconds is actually a good sub-exposure for this camera under these circumstances. And they're all different. But you don't really want to use a 6-second exposure. Eventually, I was able to make images like this. This is Cygnus. On the left side is the North American Nebula. No, backing up just a second here. The reason I went through this exercise is what I really had in my mind of doing someday was getting an awesome image of a comet. I wanted to get an epic image of a comet, and a DSLR is a good way to do that, a big, bright comet. And I didn't know if a big, bright comet was going to come along tomorrow or a decade from now, but I wanted to be ready. So remember that. Another thing that people don't think about is read time. Read time is how much time passes between the end of the exposure and the beginning of the next exposure. And there can be a lot of reasons for that. It may not just be read time, but there is this minimum amount of time that it takes to read out the exposure. Some modern cameras do it very, very quickly. Some of the older CCDs take time. So let's imagine a 30-second exposure with a 30-second readout time. That means you're only using half of your time available for imaging. And that's going to cut down the amount of signal to noise ratio you're going to get for that night because you're only spending half of your time imaging. So for example, at 30 seconds readout time, 6 exposures of 10 minutes is going to give us a total of 60 minutes exposing and 63 minutes overall. But 120 exposures of 30 seconds are going to give us the same 60 minutes of exposing, but it's going to take 2 hours. That's something that's always going on because for most cameras, because there's this time between exposures. If you want to maximize your signal to noise ratio on a given night, there's usually a limited amount of time. We saw earlier that with the Helix, it was only going to be best between 4:30 and 5:30. That's an hour. We don't want to be throwing away too much of that time by using too short of an exposure. So the other thing is that sub-exposure time determines how your stars appear. So longer exposures are going to produce larger stars in general. And then you're going to run into things like saturation, blooming, and clipping. My little diagram here. Over here on the left, we've got just 1 pixel or detector well in the camera. Photons come in, they hit that, they knock off an electron, most of them do. And then we count the number of electrons, and that's our signal. The problem is that detector well can only hold so many. So you're going to reach the point where it's going to be full. So if there's too much signal, it'll be full. That means it's saturated. And if it's more full than that, it'll start spilling out over the edges like it shows here. And that will produce blooming. You can see on the right an example of blooming stars. The signal is spreading out into neighboring pixels. And then when it's read out, it makes these big streaks. There's one more thing, and that is called clipping. And that's when the signal count is too large to store in your detector memory. So usually if like a 16-bit detector can store numbers up to 65,535, and if it's greater than that, you can't store it, and that's called clipping. You have to take all of these things into account when you're trying to make a nice image, that your sub-exposure time isn't too long, that you run into these problems. This is particularly a problem with modern CMOS cameras. You will see online, and people will talk about this in places like Cloudy Nights, the idea of an ideal exposure. And they do this by determining the point where the sky brightness overwhelms the read noise. And this is a useful thing to do if it's all you can do, but it's actually very limited. It only focuses on those two things, the sky brightness and the read noise, and there are a lot of other things going on. But more importantly, what you can end up with is it'll say something like, well, your optimum sub-exposure is 1 minute, and it turns out the 2 minutes, 5 minutes are so close to being the same number that you can use any sub-exposure you want. That actually happens pretty often, but these calculators, the algorithm they use, don't have any way of telling you that. So you just get a number. Well, I've got to use 1 minute sub-exposures, but it might be that you get a lot better images at 5 minutes. So this calculator approach doesn't work that well. If you can already calculate the signal to noise ratio of the final result, what you can do is you can just say, okay, over a period of time, say an hour, what sub-exposure can I choose that will give me the most signal to noise ratio? You can just try a bunch, try 60 seconds, try 120, whatever, see which one gives you the highest signal to noise ratio. And that's what SkyTools can do. But remember, there's all these other things going on, like aesthetics, and how many faint stars do you want in your image? Do you want lots and lots of them? You're probably going to want a longer sub-exposure. So there's a lot of things going on. If you use a longer sub-exposure, you could end up with blooming and clipping and these other problems with brighter stars. So it's best to you're going to have to insert yourself into this. There's no button that you can press that'll tell you the best sub-exposure. It'll tell you the best sub-exposure for certain things, and then you're going to have to sort of decide what you want. One of the things that you might want to do is if you're doing multi-band, multi-filter astronomy or imaging, here's an LRGB set. This column over here, well, this column here tells you the exposure time that's required on this very faint object to reach a target signal to noise ratio of 20. And that's, I think I somehow skipped over the slide that tells us what a good signal to noise ratio number is. But 20 is a sort of good image. It's not going to be great, but it's going to be sort of good. And the software will help you with those things, with definitions. It means it's going to take 3.3 hours in just the luminance, and in the other filters, it's going to take much longer. And one thing you can do is you can use 2 times binning on the other filters, which will bring them down to closer to the luminance. That's just one technique. This can tell you what an effect that's going to have, what effect that's going to have. But I really wanted to look at this R stars column. It finds the filter with the most throughput that produces the most signal. In this case, it's the luminance, sets that as 1. And then these numbers over here in the R stars column for the other filters tells us how much longer you have to expose in order for a typical star to be about the same size with the same signal on your image. That will make it, if they're comparable, it'll make it a lot easier to combine them to get nice looking stars later on. So what this is saying is that generally you want to expose around 4 times longer for your RGB in order to get similar sized stars. Now you can control that to some extent in your processing, but sometimes things get wild enough that it's really hard to control. So getting back to review a little bit before we do an example, how the workflow works in SkyTools. Now that we have these things that we can calculate, we get back to the workflow. And so the first thing to do is select an appropriate target for your imaging system, or select a target and find the appropriate imaging system for it. If you're lucky to have lots of telescopes, like say iTelescope. Then you create an imaging project that defines the goals for your project. And then you select a night to image. And then you use the scheduler to determine the best time of night to start your imaging. And then from that, you generate a plan. And then you can upload that plan to the telescope, make a reservation, attach the plan to it. Then download your images and log them into SkyTools. And I'm going to do sort of an example of that. We do it on time. And then finally, you add observations to reach your exposure goals, because you could set your exposure goals and say, I want a signal noise ratio of 60. So you can just keep adding observations, and it will look at the quality of the observations as you add them, or your images, I mean. And once you reach 60, it'll say you're done. Oh, jumped ahead. This is where I'm supposed to go. Okay. So this is SkyTools for imaging. And this is the target selection tool. This is the start of the process. So what I'm going to do is I'm going to turn on a couple of filters. I'm going to turn on the filters that filter out objects. This is just the Messier list. Filter out objects that aren't great for this imaging system. I've chosen T2 at New Mexico Skies. And I'm going to filter out objects that aren't great tonight. So that leaves me with a selection of objects. I've also chosen an image scale grade of B, so that's going to be pretty good image scale. And right off the top, we can see that black eye galaxy looks like a pretty good target object. I'm going to open an atlas. Oops, opened on the wrong monitor. So here's the atlas view, and I've already downloaded a digital sky survey image so we can see what it looks like. So that's going to be a nice object. So I'm going to go ahead and create an imaging project for it. So I'm going to right click on it. And then I'm going to choose create new imaging project for the black eye galaxy. Most of this stuff stays the same from one time to the next. If you're tracking a comet, you can tell it that I want to track the target, that sort of thing. Then you move on to the composition and tiles. And this is where you choose the composition. I could move this to here, and that's where the image would be taken. I could do that if I wanted to, but there's not a lot going on here, so I'm just going to leave it in the middle. If it was really big and filled the field of view, I could use this tool to create tiles that would cover the whole thing. And I can also show that image in the background. So now that we've got that done, we move on to the exposure goals. This is a color camera, so there's only one filter. And let's say I want higher picture quality of 30. It says it's going to take 18 minutes under ideal conditions to reach a target signal noise ratio of 30. Well, now we're done. So we'll go ahead and press done, and we've created an imaging project. That's what this P here is for. Now, this is a simple example of one object, but this works best if you actually create imaging projects for a whole bunch of things and don't even care what time of year they're best at. And then you use the scheduler, and the scheduler will list a bunch of things over here and tell you which ones are best tonight. But we've only got one object, and that's this black eye galaxy. Notice I've got set for T2 again. It's for tonight, and that's odd. What happened there? And New Mexico skies. I must have changed that somehow. So here's our black eye galaxy. Remember we talked about this graphic at the top here. This bright green section between, say, I don't know, 9:15 and 1 a.m. That's the best time to image. And it is saying, let's just go ahead and start at a little after 9. And I'm going to schedule it. I'll just click add, and it shows up in the schedule over on the right. Change my plan settings. Let's plate solver images. We'll leave the focusing alone. So we've just got one object, and it says to start at 9:11 and to go, it's going to go for about 30 minutes. So the next thing I can do is click Save Plan. And where'd it go? It should have popped up. There it is. And this is the plan it generated that iTelescope can use. And it put the plate solve in there that I suggested. And it knows ahead of time that this telescope needs to auto guide. And it just tells us that we're going to do 5 300-second exposures. Down here, it tells us the amount of time and how much of an hour, so we can figure out how much it costs if we want to. So the next step is to go to the iTelescope website. And I was going to do 2 of these examples, but it would have been time consuming. Other than uploading stuff to iTelescope, the process for a backyard telescope, even my DSLR, works pretty much exactly the same. So I'm just going to do an iTelescope example. So we're going to use T2. So I'm going to select T2 here. And then we're going to go down to Upload Observing Plan. I'm going to select Download Existing Observing Plans. And then I'm going to choose my file. It's this one at the top. And I'm going to upload it. Refresh, and sure enough, it's down here, the May 20th one, and this is our plan that we created with SkyTools. So, what did I do? I closed the wrong window. Well, that was a problem. Hold on just a second. Went ahead and closed my browser. Sorry. All we need to do next is set it up for a given night. What am I doing here? Oh, I'm on the wrong. This is why I had it set up ahead of time. There we go. All right. We'll be back to it here in a second. Mexico skies, T2, apologize for this. The bar for the zoom covers things up at the top. It makes it hard to navigate. Sometimes I clicked on the wrong thing. So we already uploaded our observing plan. So the next thing we want to do is create a reservation. I'm going to go to make a reservation. And by the way, for these telescopes that don't require net reservations, you can do the same thing. You just start your plan live without a reservation. And going back to what SkyTools said, it said start at 9:11 and go for about 30 minutes. And by the way, SkyTools looks at all the different kind of things and how long they take for this telescope, changing filters and so forth, and slewing and all that, and comes up with a fairly accurate version of how long this is actually going to take. So 30 minutes starting at 9:11. So this is tonight. And notice it's saying I can start earlier. That's a trick. I'm going to start at 9:15 and go to 9:45. And then select my plan for tonight. Click Confirm Reservation. And here's my reservation. So now the telescope will just go ahead and do it. And once it's done, I'll download my image. Then I will open my imaging project. And I'll go to the Observations tab. I'll click Add New Observation. And then I'll click this button and browse to the actual image. Obviously, I haven't downloaded it yet. And it will read the FITS header to determine the exact time and so forth. So you don't really have to fill out all this stuff up here. It'll fill it out for you. At least everything that's in the FITS header. You might have to put in the temperature and the humidity if you want. And it's from this that it keeps track of your observations. So you'd enter that and it shows up in here. And then the next night, if you hadn't completed it, it'll say, okay, you need 2 more 5-minute exposures to finish it up. It'll take that into account. in the scheduler. So that's the process for using it in iTelescope. And just quickly look at a couple images that I've taken. I call this my iTelescope budget image. It's 2 5-minute exposures in the red and the blue filters. So this is as cheap as you can get, and there's no stacking involved. And the way you do this is when you go to process the image, you calculate the green filter as a 50-50 mix of the red and the blue, and this is what you get. This was a cool day. September 10th, 2019. I follow the Comet online group, and it was announced that there was a possible interstellar comet. So I'm thinking, well, I got to image this. I got to image this right now. What SkyTools allowed me to do was very, very quickly figure out which telescope I should use and which one would work. And my first choice was T21, but it was scheduled, but T11 would work pretty well. So I scheduled 30 minutes on it. And this is what I got. I got 3 10-minute exposures. The reason I used 10-minute exposures is I wanted to detect as much as possible so that we could see a little faint fuzz around it, see that it really was a comet. So on the right is a stack of the 3 10-minute exposures with the stars trailed. And on the left is the comet moving from exposure to exposure. The stars are trailed because it's a 10-minute exposure. So that was fun. And I was really glad I had SkyTools because it allowed me to get on that right away and get it as quickly as possible. Here's another image that I took. This is 2017, and it's 60 12-second exposures with T11. And I stacked them in Astronomical. And there was a 30% discount for the moon and a 60%, the moon was 60% illuminated and at an altitude of 35 degrees, but I figured SkyTools told me I could still do it. So, but because there were 60-second exposures, I was charged for 20 minutes of time. This cost me $33, which I think is a pretty darn good deal. And the trick to this image, or this movie, is that during the 60-second exposures, this thing was moving so fast, this is a near-Earth asteroid, that the stars actually trailed a little. So when we follow it, the stars are elongated a little bit, which gives you this sense of motion. And lastly, remember way back when I said when I got my DSLR, I had in mind an epic photo of a comet. Well, what happened in 2020 was an epic comet. And so just a few months after I bought my camera and figured out how to use it and bought the tracking mount and figured out how to get good results with that, the comet came along and I got this image from here on the mountain. At first, I wasn't too happy about the clouds, but I captured this lightning. So I think this is a pretty special picture. I really thought it was going to take me 10 years to get an image like this, but there it is. The trick is I was ready for it. And that's really what SkyTools is all about, is being ready to get good images. And that's pretty much it.